Assalamu alaikum students. So today we are going to start our chapter number 8 from Munson book, and chapter number 8 is related to the viscous flow inside the pipes. So whenever a fluid flows inside the pipes, it will encounter some resistance, and due to that resistance, our flow will act like a viscous flow. So a viscous flow is basically a flow that will have a certain amount of viscosity. And as you can remember from our FM1 course, Fluid Mechanics 1 course, we have already covered what viscosity was and already in the introductory lecture 1. So again, if we just revise it, viscosity is the fluidity of the fluid or the resistance of the fluid to the change in its shape. So if a fluid is showing a lot of resistance to the change in its shapes, then we say that it has a high viscosity, and if a fluid is showing less resistance to the change in its shape, then we will say that it has low viscosity. A simple example, as you will already know, is of honey and water. Honey has high viscosity and water has low viscosity. So what we are going to do in this chapter, we are going to see the flow inside the pipes, and we will see what kind of resistance the fluid will have when it flows inside the pipes. So let's move on. So let's talk about a pipe system, but before that, let's look at the definition of a pipe. What will be the definition of a pipe if we would like to define it? So a pipe is actually a closed conduit of a circular cross-section. So that is the engineering definition of a pipe. And you will also have come across a term called duct. Ducts are normally used in refrigeration when we like to circulate air inside a building, so hot or cold air. So we use ducts. And what is the definition of a duct? So a duct is a closed conduit of non-circular cross-section. So anything closed or with a circular cross-section will be called a pipe. You will have come across a lot of pipes in your daily life, and if you have visited some hospital or mall, you will have come across ducts or that are used for refrigeration purposes. And the definition of a duct is that it has a non-circular cross-section. Normally it has a rectangular or triangular or other than circular cross-section. So this will be the difference between a pipe and a duct, and that can be a good reasonable engineering definition of a pipe. So what will be a pipe system? What is a simple pipe system comprised of? So let's look at that. So this is a pipe system, a typical pipe system. If we would like to add energy to our fluid, so we will install a pump, and what will this pump do? It will actually transport a fluid from this reservoir from low potential to this reservoir that is at a high potential. So this is actually adding energy to the fluid by using a pump. So we are talking about a pipe system. So a pipe system will comprise of pipes. So these are the pipes. These are the pipes that are being used in this pipe system. This pipe system will also use connectors. So to arrange these pipes in different directions, in different orientations, we will use elbows, we will use tees. These are the normal components that you come across. And to add energy to this fluid inside this pipe system, we will use a pump. And to control the flow rate, we will use a valve. So this is the basic pipe system. You are familiar with this. You can see it in your homes. And it is actually, what this pump is doing is it is actually adding energy to the fluid. We also know that we can also install a turbine here. We can also use a turbine, and what that turbine will do, it will actually extract energy from that fluid. So pump is actually adding energy to the fluid, and a turbine will extract energy from that fluid. So this is a basic pipe system, and this is the difference if we install a turbine or a pump to a piping system. So let's move on and let's clarify ourselves about an open channel and a closed channel. So a closed channel is a pipe that is completely filled with a fluid, and the only way to transport fluid in this closed channel is actually with the help of a pressure difference. So if this is point 1, if this is point 2, the fluid will flow from point 1 to point 2 if there is low pressure at point 2 and high pressure at point 1. So this is actually a closed channel. This is a closed channel. This is a pipe flow, and this is an open channel. An open channel is the one which is not completely filled with fluid. As you can see, it is half filled with fluid and half it contains air. If you can suppose, you can see these types of open channels in your drainage system, and that is used to transport sewage water or flood water or rainwater from the roads or streets. So that's where these open channels are used. Open channels are not completely filled with fluid, and pipe flow or closed channels are those that are completely filled with fluid. And in this pipe flow or a closed channel, we need pressure difference to transport the fluid from one point to another point. And in this open channel, we cannot actually control it with pressure difference. What we will use gravity. In this case, we will use gravity to transport fluid from one point to the other, because it is open. It is as you can see, multi-phase. It is also liquid. It also contains gas. So it is open channel. It contains both water and air, and again it is used in sewages, in transporting the flood water or the sewage water from the streets or the roads. So for that purpose we use open channel flows. So and on open channel flows we use gravity to transport the fluid. So this is the main difference between a pipe flow and an open channel flow. So after clarifying ourselves about the pipe system, now let's talk about the flow that can occur inside the pipe. So as you can see that there can be two types. One is laminar and the other is turbulent flow. So to clarify ourselves with these terms, we will use the experiment that Osborne Leonard did, a British scientist and a mathematician. And what he did, he actually injected a dye streak. And what is a dye streak? He actually injected ink inside a pipe, and then he observed this dye streak. This is a dye streak. He observed this dye streak by changing the flow rate inside the pipe, and he observed the pattern or the shape of this dye streak by changing the flow rate, and he identified three regions. He identified three regions. In the first, as you can see, in the laminar region, are at low flow rates. At low flow rates, he observed that the dye streak does not change. The dye streak does not show any disturbance. That was at low Q or low flow rate. Then by increasing the flow rate a little bit more, he observed some disturbance as the dye streak traveled along the pipe. He observed some disturbance. He called that region a transitional region. And then as the flow rate was very high at high Q or high flow rate, what he observed a lot of disturbance, and he called that a turbulent region. So instead of flow rates, he came up with a term, and he named that term after himself, and he called this a Reynolds number. We already derived this number in Fluid Mechanics 1 course in our dimensional analysis chapter, when we said that we can, with the help of dimensional analysis, we can come up with different dimensionless number, and Reynolds number is a dimensionless number. It does not have any dimensions. If you can already experiment with this, if you put the dimensions of density, velocity, diameter and viscosity, you will come up with a dimensionless number. So the collection of this density, velocity, diameter and in the denominator, that is viscosity, we call this Reynolds number. So if we know our density, velocity and diameter of our pipe and our fluid, respectively, and we know our viscosity of the fluid, then we can calculate our Reynolds number. And he identified some values of the Reynolds number, with the help of which we can identify that either the fluid is laminar or turbulent. And for laminar flows, he identified this number, that if Reynolds number is less than 2100, then that flow is laminar, and if a Reynolds number is greater than 4000, then that flow will be turbulent flow. So these are the actual values with the help of which we can identify that whether our flow is turbulent or it is laminar. And in between these two values, between 4000 and between 200, lies a transitional region. So let's say if our Reynolds number values come out to be 3000, then it will be a transitional region. It will not be completely laminar, it will not be completely turbulent, but it will be a sort of a combination of laminar and turbulent flow called the transitional flow. So this is what Reynolds did. With the help of Reynolds number, we can now easily identify that whether our flow is laminar or turbulent. So we are more concerned about the flow development of a fluid inside the pipe. So what we are going to do, we are going to consider a pipe. This is our pipe, and inside that pipe we are going to pass some fluid. So let's say that there is a fluid that is entering the pipe, and what will be the velocity profile of this flow inside this pipe. So at initially this profile will be uniform. This will be uniform. So this is the entrance region. This is the entrance region. So at the entrance, this velocity profile will be uniform. But as it moves along this pipe, this will tend to become parabolic. Why will it tend to become parabolic? Here you can see from the length of the arrows that here at the entrance region, the length of the arrow is uniform. That's why this is called uniform profile. This is uniform. But here the length of the arrows is not uniform, it is changing. And it is changing from the edge of the pipe to the center of the pipe. So what we can deduce from this is that at the edge of the pipe, the flow velocity is becoming zero. Almost it is becoming zero. And at the center of the pipe, the flow velocity is maximum. This is due to the no slip condition. The no slip condition. So due to the no slip condition, what is a no slip condition? We have already discussed this, that when a fluid comes across a solid boundary, what the fluid particle does, that due to friction, the particles stick to the solid boundaries. So that's why this is what is happening here. The fluid particle is sticking to this solid boundary due to friction, and due to that the velocity of that fluid particle is getting low. And as there is no solid surface at the center of the pipe, here the velocity is maximum, and at the edges of the pipe the velocity will be low. But again, this flow is not fully developed. This velocity profile is not the final profile of this flow inside this pipe. As we move along, this will be the actual profile, actual velocity profile of this flow. Here now you can see that at the center the velocity is maximum, and at the edges the velocity is completely getting equal to zero. So this is a parabolic profile. This is a parabolic profile, and this is what happens when a fluid flows inside the pipe. It goes through this transition. At the entrance it is uniform, but during transition it gets into this shape. It gets into this shape due to the no slip condition near the boundary of this pipe, due to the friction between the fluid particle and the solid surface. And as it moves along, it completely changes into a parabola. This velocity profile completely changes into a parabola. So this is now a completely developed flow profile inside the pipe. Now let's look into more detail. and let's identify some regions. So this is what this is. This is again the entrance region. This is the entrance region. As the fluid enters, it is having a uniform profile, but as it travels due to friction between the fluid particle and the solid surface of the pipe, its velocity profile is changing. And as you can see, this blue region, that is the inviscid core. What is inviscid? Inviscid is actually having no or very low viscosity. So it does not have any resistance to the flow in the center of the pipe. So that is why the inviscid core lies in the center of the pipe. The center of this pipe has the inviscid core. And then we have boundary layers. We have already defined boundary layers, and a boundary layer is a layer from this point up until the point where the flow becomes inviscid. So from the point where the fluid velocity is 0 up until the point where the fluid attains maximum velocity, this region is called this layer is called the boundary layer. This is called the boundary layer, and as you can see, the boundary layer is increasing and increasing, and as we can move along, we comes to a region where our velocity profile is fully developed. So now this is a fully developed flow. This is a fully developed flow, and this right here is a developing flow, and up until this region, this is developing. So this is what we are more concerned about. We have actually identified two regions. One is a developing flow region, and one is a region where the flow has fully developed. So again, to go through it, we have an entrance where the velocity profile is uniform. You can see from the arrows they are of equal length, but as it moves along, it moves through its shape changes, and as you can see, the length of the arrows changes, and this shows the velocity near the edges of the pipe is becoming reduced, and as it moves along, it completely changes into the parabolic shape, and this actually shows that the velocity near the edges of the pipe has come to 0 due to this boundary layer, and at the center we have a maximum velocity. So when our fluid attains this velocity profile, then it is a fully developed flow. Why we are more concerned about this fully developed flow? Because a fully developed flow is actually uniform in shape. It is uniform in shape, and a developing flow is actually in transition. This is actually in transition. It is changing continuously, and we cannot easily deal with a flow that is continuously changing. So we are more concerned about a flow that is fully developed and whose velocity profile will not change as it moves along after it has fully developed. And when will it not change? It will not change after this entrance length. After this entrance length. So we identify a length that is called the entrance length, and after this entrance length, our flow will become fully developed. Our flow will become fully developed, and we have actual formulas to calculate this entrance length for a piping system, and these are actually dimensionless formulas. And as you can see, this is LE is the entrance length over D is equal to 0.06 RE, that is the Reynolds number for laminar flow. This formula is for laminar flow. So let's say our laminar region is RE is less than 2100. This is where our laminar region is. So if the value of Reynolds number is less than 2100, we put the value of Reynolds number here, we will get our value of LE, and that will tell us that after this much length we will have a fully developed flow. And again, for turbulent flow, we have this formula. These formulas are experimentally calculated. So with the help of experiments, we have came up with these two equations. And for turbulent flow, we have this equation for our entrance length, and again it is LE over D is equal to 4.4 Reynolds number to the power 1 over 6. So turbulent region, in turbulent region, our Reynolds number is greater than 4000. So if we put a value of Reynolds number greater than 4000 here, we will get a length LE, and after that length we will actually get our flow that will be fully developed. So why we are concerned about the fully developed flow? Because a fully developed flow is uniform in shape. As you can see, its shape is uniform, it will not change again, it will remain like this velocity profile will remain like this throughout the length of the pipe, and we can actually deal with this easily. And with the help of this velocity profile, we will be able to calculate our velocities inside this pipe, our flow rates and our head losses. So by dealing with a fully developed flow, because again we cannot actually deal with a flow in transition because it is continuously changing, and we cannot actually apply mathematical equations in a transition region or in a developing flow region. So what we do, we calculate a length after which a flow will be fully developed, and then we apply our mathematical equations and actually derive our velocity, our flow rate and our head losses equations. So let's move on to that. Now let's see what the fully developed laminar velocity profile will be and what will be its characteristics. So a fully developed laminar velocity profile will be constant in time. As we move along a cross section of a pipe after the flow is fully developed, the velocity profile will be constant. It will be parabolic and layered, and speed has axial component only, means it will only, the speed will only change along the x-axis or along the axis of the pipe, and the speed will vary along the radial direction, means the velocity profile will only change along the radius of the pipe. As you can see that here this profile will be, first it will be constant as we move after the flow is fully developed, as we move along this flow, and it will be parabolic. As you can see, it is parabolic, and as you can see, it is layered, because it is laminar, and speed has axial component only. You can see that the velocity has only axial component, and it is only changing along the radius of this pipe. As you can see that it will only change along the diameter or the radius of this pipe. So the speed varies in radial direction only. This is for the laminar velocity profile. Now let's see that what a fully developed turbulent velocity profile will be, as you can expect, it will be very unpredictable because it is turbulent. So it will be very unpredictable for us to comprehend it or to make it a constant in time, and it will be three-dimensional, it will not be one-dimensional. So if we take a velocity, so the velocity will be in three dimensions, not only in one dimension. So it will have Vx, Vy, Vz, all three components. The velocity will have all three components. It will have the axial component is the largest, so the velocity along the axis of the pipe will be the largest, and it contains eddies of various size, means it will contains eddies. Eddies are the disturbances inside the fluid, so it will have a lot of disturbance. So let's look at the turbulent velocity profile at an instantaneous time, means at a specific time its profile will look like this, but because it is turbulent, it will be changing, it will keep changing. As you can see, now it's become parabolic, now its shape is changing, as you can see. So as stated, it varies unpredictably in time. So to deal with this, what we will do, we will take the average of all these profiles, of all these non-common or uncommon profiles, and we will come up with an average profile, and we will use that for the turbulent velocity profile. So for time average fully developed turbulent velocity profile, these are our assumptions as we do in fluid mechanics. So this is how our velocity profile will now look like. If we take the time average of all these turbulent velocity profile, this is how it's going to look like, and what will be its properties. It will be constant in time, as you can see, because we are talking about a time average velocity profile, only has axial component and varies radially. It only now will have a velocity along the x-axis, and that velocity will only change in the along the radius or the diameter of the pipe. It has a flattened center. And what is a flattened center? This here, right here, this right here is a flattened center as compared to this. As compared to this, that have a parabolic center. And large velocity gradients near the wall. It will have large velocity gradients, as you can see that from this arrow, that it is near the wall, but it is again very large. And as you can see from here in the laminar flow, that near the wall the velocity gradient is decreasing, but here in turbulent flow the velocity gradient is large near the wall too, because it is turbulent. So the friction will not that much, the friction between the fluid particle and the wall will not be that much greater, because this is a turbulent flow. It will have very high Reynolds number, and we have assumed this profile for turbulent flow, and these are the characteristics of this turbulent velocity profile, and this is what we are going to use in our analysis. But before that, we will use our laminar velocity profile, and we will use it to calculate pressure drop, velocities, flow rates and head losses. So first we are going to use this velocity profile. So now, after developing the velocity profiles of laminar flow and turbulent flow, let's look at the fully developed laminar flow profile, and let's see how we can use that to derive some equations for our pressure drop, for our velocity and for our head losses. So the knowledge of velocity profile, as we already discussed, leads directly to the useful information, and that useful information is pressure drop across the pipes, the head losses that occurs inside the pipes, and the flow rates inside the pipes. And we will now develop equations for velocity profiles that are full laminar. And by full laminar, we means that the velocity is uniform, that our velocity is uniform. And by uniform velocity, we say that there is no acceleration, so acceleration will be equal to 0. And as you already know, by laminar flow, we know that by having a laminar flow profile, that we will only have the x component of our velocity. We will have only the x component of our velocity, and that x component of velocity will be the function of the radius of our pipe. So that velocity profile will change along the radius of the pipe. So these are our initial assumptions for this laminar flow. And now let's look at this diagram. As you can see, we have identified a fluid element, that is this fluid element, and this fluid element has a length of L, and it is inside a circular pipe. So this is a circular pipe, and as you can already see, this is a laminar velocity flow profile, and we have only the x component of velocity, that is the function of radius r, because the velocity profile changes along the radius of this pipe. So our first assumption was that our velocity is uniform, acceleration is 0, and the velocity component is only the x velocity component, and it changes along the radius of the pipe. So if we are going to take this fluid element right here and draw it here, so as you can see, the velocity is in the x-axis only. There is only the x component of velocity. So the forces that will act on this fluid element will also be in the x-axis, in the positive x-axis or in the negative x-axis. And if we can apply the Newton's second law on this fluid element, then we have already established that this is a uniform flow and acceleration is not changing, velocity is not changing, so there is no acceleration. So our F is equal to 0. The summation of all the forces on this fluid element will be equal to 0. So using this equation, we will add all these forces that are acting in the positive or negative x-axis, and we will see what we will get. So let's add all these pressure forces. Let's look at them first. This is the section 1 of this fluid element. This right here is section 1. This right here is section 2 of this fluid element. Here P1 pressure force is acting on this face. So as you know, pressure is equal to force per unit area, the normal force per unit area, and here it is written as F is equal to pressure into area. So all the pressures are written in the force term. Similarly, as it is point 2, and we have already discussed that flow will occur inside the pipe if there is a pressure drop or due to gravity. So we are not considering gravity here because we are not considering the mass of the fluid here. So there is only pressure drop. So if the pressure changes from point 1 to point 2, so what will happen? We will for the flow to occur in this direction, pressure at P1 must be greater than pressure at P2. So at P2 there will be a change in pressure, that is P1 minus P2, and for P2 our equation will be P1 minus delta P. So this will be the equation for pressure at section 2, as you can see right here, multiplied by the area because it is written in terms of force. So these are the forces, and on the lateral surface you can see a shear stress, because due to the viscous forces there will be shear stress on the lateral surface of this fluid element. So let's look at the shear force and try to write it in simple terms. So shear stress is also equal to force per unit area, and this will also be written in terms of forces. So F is equal to shear stress into area, and here the area is the cross-sectional area, so it will be multiplied by the circumference of the circle and the length of this fluid element. So tau will be equal to 2 pi r, that is the circumference of a circle, multiplied by the length to get the cross-sectional area of this fluid element. So these are the forces acting on the fluid element, and now let's apply the equation, that is summation of all the forces is equal to 0 on this fluid element, and see what happens. So this is the equation that we will get. This is the pressure force at section 1 minus the pressure force at section 2 due to the negative x-axis. It is directed along the negative x-axis, and here is the viscous, the shear stress that occurs on the lateral surface. It is also directed along the negative x, so that's why there is a negative sign here. So we will arrange this equation. And as you can already see that we can cancel out some terms if you open the brackets. So what we will get our equation for the pressure drop. This will be our equation for the pressure drop, and we can refine this equation further and write it like this, that pressure drop is equal to length multiplied by the shear stress multiplied by 4 divided by the diameter of the pipe. Here r is replaced by r is equal to d by 2. So this is why this equation looks like this. So this is our equation for pressure drop inside the pipe for laminar flow, and as we already discussed, the basic horizontal pipe flow. This is a horizontal pipe flow. A basic horizontal pipe flow is governed by a balance between viscous and pressure forces. So this is a balance between the viscous forces, these are the due to the shear stress that occurs, and the pressure drop, the pressure forces. So this is our basic equation for pressure drop inside the pipes. So now what we are concerned about is the velocity profile. What will be the equation for a velocity profile of a laminar flow? So to do that, we will use our assumption that we covered in our introductory lecture 1 when we studied viscosity. And in viscosity we introduced ourselves to Newtonian fluids, and what we derived with the help of a simple experiment, that in Newtonian fluids the shear stress is equal to the strain rate. this is the strain rate, and this is the viscosity, and this is the shear stress. So Newtonian fluids generally follow this equation. So our fluid is Newtonian fluid. So we will take this equation and we will try to develop now an equation for our velocity profile. So this is our equation for the pressure drop, and as you can see there is also a term for shear stress right here. So if we use this equation, we can actually exploit this derivative right here, this velocity profile du over dy, to get our equation of velocity profile. So this is the equation for Newtonian fluids, that is the shear stress is equal to the strain rate multiplied by the viscosity. The negative sign explains that the velocity actually decreases as the shear stress increases due to the viscous forces. So the negative sign here shows the increase in the decrease in the velocity. So now let's use these two equations and develop an equation for our velocity profile for laminar flow. And by combining these two equations, we obtain this equation right here. What we did, we actually took the value of shear stress, that is the value of shear stress, and we put it right here instead of this shear stress. So we substituted the value of shear stress in this pressure drop equation, and we got this equation right here. This is the velocity gradient right here, because the velocity changes. Velocity is the function of radius. As it changes along the radius of the pipe is equal to negative pressure drop divided by 2 times viscosity into length of the pipe multiplied by the radius. So now we can actually use our integration, and we can derive an equation for this velocity profile for laminar flow. So let's do that. So what we will be getting equation for a parabolic velocity profile, as we already discussed that the laminar flow profile, velocity flow profile is parabolic in shape. So as you can already see, we derived an equation that was in this shape initially, that is du over dr is equal to minus delta p divided by 2 mu L into R. So what we did, we shifted dr right here, and we can now integrate this and get our equation for velocity profile for laminar flows. So let's do the integration, and this is what we will get. It is a simple integration, so we will get from here r squared divided by 2. It will be put in this equation right here, and we will also get a constant plus c1 because we integrated this equation without limits. So whenever you are doing integration without putting the limits for your integration, then you will get a constant. So to get the value of this constant, what we will do, we will actually take velocity. This is the pipe. So to make you understand this, let's say that this is our velocity flow profile. This is our parabolic velocity flow profile. So as you can see, this is the center of the pipe. This is the center of the pipe. So in the center, the velocity will be maximum. There will be maximum velocity at the center. But here this is the r value. So here at the center, velocity will be maximum, but the radius of the pipe will be 0 at this point. If you take this point A, so r will be equal to 0. So here radius is 0, but velocity is maximum. But if we move near the walls of this pipe, so here the radius will be maximum. It will be equal to r. So here the radius is maximum, but velocity will be 0 due to the no slip boundary condition. Here the fluid particle will stick to this wall of the pipe, and if we take our velocity as a function of radius r, so it will come out to be 0. So if we take this condition that u of r is equal to 0 and put it right here, that here our velocity is 0. So what we will get this equation like this, that is plus C1. So now we can actually write the value of C1, and C1 will be equal to delta P divided by 4 mu L into R square. So this will be the value of C1. So that's our assumption, that at the edge of the pipe there will be zero velocity. The velocity will be zero due to no slip boundary condition. So we put that condition here in this equation and derived the value of C1, and now this will be the value of our C1, as you can already see. So this is due to the no slip boundary condition, and this is the value of C1, and now again we will put this value of C1 in this equation right here, in this equation right here again. So we will get this equation. Now this is the equation for parabolic velocity profile. This right here is the equation for parabolic velocity profile. Actually you get this equation by writing this minus delta P over 4 mu L into R square plus C1. So the C1 value is right here, that is delta P over 16 mu L d square. So what we do, we take this term, this whole term, and then we multiply, divide both these terms by exact this term. So when we do that, we actually get this term right here. So you can solve that and you will get a similar answer. So, or you can take that term common, same thing, is the same operation. So you will get equation for parabolic velocity profile, and we can further simplify that, and we can actually write that this velocity right here, this velocity right here is the velocity at the center, because when we solved that equation for the constant C1, what we assumed that the velocity right here is 0. The velocity right here is 0. Why it is 0? Because we assume that this is the velocity near the boundary, near the wall of the pipe. So we put that velocity is equal to 0. So we got this value, and this is the velocity for the velocity in the center of our profile, the velocity at the center of the pipe, which is the maximum velocity. So this is called the maximum velocity at the center of the profile, and overall this equation right here, or this equation right here, is the equation for parabolic velocity profile. So this was our equation for our velocity profile. Now what we are more concerned about, we are concerned about the, okay, this was the initial equation that we integrated. So now we'll move on and we will derive an equation for our flow rate. And to do that, we will take this cross section. This is again the cross section of our circular pipe. We will take this element right here, this fluid element right here, and this fluid element has a radius of dr and an area of dA, which is equal to 2 pi r into dr. Here the radius at the center will be 0, and as we move from the center, away from the center, it will be maximum of r at the circumference. So now we already know the flow rate equation from your previous course, Q is equal to AV. So we will take the differential area and the differential volume in this case. So sorry, this is the velocity, this is the area. So we will take the differential area, and the velocity will be the x component of our velocity, because we are dealing with laminar velocity flow. So this will be our equation for our flow rate. This is our velocity and this is our differential area. We can write it like this. If we take the velocity profile for our laminar flow and we put the value for our dA, that is 2 pi r into dr. So this will be the equation for flow rates, and if we integrate this from this point where the radius is 0 to this point where the radius is maximum r is equal to r. So we can do that, and we will get this term right here. And by opening these brackets and applying this integration on this whole term, what we will get r square divided by 4 from this integration. We will get r square divided by 4, and multiplying this right here, 2 pi Vc. So this will cancel out, and we will get pi Vc r square divided by 2. So this is how we are going to solve it. So this is what we just wrote. This will be our equation for the flow rate. You can actually put the value of our velocity that is at the center of the profile, which is the maximum velocity. So we see by substituting this that Vc is actually equal to delta p d square divided by 16 mu L. So by putting this value right here, you will get your equation for the flow rate. So this is our equation for the flow rate for laminar flow inside a pipe, and this is also called Poiseuille's law. It is a scientist and a mathematician who derived this equation for measuring flow rates for laminar flows inside the pipe. And by laminar flow, we mean that the Reynolds number should be less than 2000. So in this range, you can use this equation to find the flow rates inside the pipes for Newtonian fluids, as we already mentioned. Then we have already have an equation for our velocity profile. We already have an equation for our velocity at the center of that profile, but what about the average velocity of that whole profile? So to get the average velocity, what we can do, the flow rate equation actually deals with the average velocity. By definition, the average velocity is the flow rate divided by the cross-sectional area. As you can see right here, that average velocity is the flow rate divided by the cross-sectional area. That is cross-sectional area in this case is pi r square. So by using this basic equation and by putting the values of flow rate and area, we will get our value for the average velocity. That will be for a laminar velocity flow profile, and this equation is obtained from this equation right here. From this equation, by putting the value of flow rates, this is the equation of the value of flow rate, and by putting the value of area. So this will be simplified to this form, and by putting the values of Vc, that is the velocity at the center of the laminar flow profile, we will get this equation. So this equation is for the average velocity, and that average velocity will be for this velocity profile, that is the laminar flow profile. So what we did, we derived equation for pressure drop, delta P, the flow rate. We saw the equation of this parabolic velocity profile, and then we saw the equation of the velocity at the center of this profile, and then for the whole average velocity of this profile, we derived this equation right here. So we derived all this by taking some assumptions for laminar flow profile. Now this was for horizontal pipes, and let's see what the assumptions are for the what we can get from these equations for horizontal pipes in which the fluid is flowing and the flow is viscous. So let's look at that. And this is the equation for flow rate, and from this equation we can see that the flow rate is directly proportional to the pressure drop. It is inversely proportional to the viscosity. It is inversely proportional to the pipe length and proportional to the pipe diameter to the fourth power, as you can see right here. And these results are restricted to laminar flow in pipes, and these are again restricted for laminar flow in pipes and horizontal pipes. horizontal pipes. We will now in the next slide see what will be the equations of pipes that are not horizontal and that are inclined, but their flow inside them is laminar. So what will be the equation of all the values that we just derived? So this is now the condition of a inclined pipe. So as you can see, the pipe is now inclined and the flow is in this direction against the gravity, and now we will consider an extra force in our analysis, and that force will be the weight of this fluid element, the weight of this fluid element right here, the weight of this fluid element right here. So we will consider that and in our analysis, and we will use the same analysis, that the summation of all the forces will be equal to 0, and as you can see, this is our x-axis, so anything inclined to this axis will be taken with an angle, just like we did with this weight right here. So what we will do, we will take the x component of this weight right here, so that will be this component to this side of this triangle, and that will be equal to W sine theta. And since we are dealing with weight, so we know a term that is specific weight, and specific weight is equal to weight per unit volume, and now we can write weight is equal to specific weight into volume. So this is how this term is written right here, and since it is W sine theta, since this is W sine theta, so we will also put sine theta right here, and since this is volume, so we will write the equation for volume of a circular pipe. So that is gamma, that is the specific weight, and volume is the area pi r square into length of the pipe multiplied by the sine theta. So this is the weight element that we are going to take in our equation, this equation, and we will do the similar type of analysis. We will add these pressure forces, these viscous forces, and we will include this weight element also in our analysis, as we wrote in equation for our pressure drop initially for horizontal pipe. And by doing that, what we will get this equation right here. This equation right here is our equation for pressure drop, and this was our equation for pressure drop in the horizontal pipe. And as you can see, the only difference between these two equations, between this equation and this equation right here, that we have now subtracted the weight term from our change in pressure. And this is what we are going to do in all our equations that we just derived. This is the equation for pressure drop, this is the equation for velocity, and this is our equation for flow rate. So wherever for inclined pipes, wherever we see the delta P, wherever we see delta P, we will subtract our weight term, that term gamma L sine theta, from the pressure drop, and we will get the respective equations. And you can actually compare these equations. On the left hand side, as you can see, this is the equation for the pressure drop, and for horizontal pipes. For horizontal pipes, and the only difference you can see is this term, that is be subtracted from this. The whole equation remains the same as this, but this is for inclined pipes. You will come up with this equation when you add up all these forces. When you add up all these forces, you will actually come up with this equation, and then you will just subtract this gamma L sine theta from all the terms in the other equations. This is the equation for average velocity, and here we will, for horizontal pipes, and to get the equation for average velocity for vertical pipes, we will again subtract the gamma L sine theta term from this delta P. So we will get our equation for average velocity for inclined pipes that have a laminar flow inside, and this is our equation for flow rate. And here from delta P, if we want to get the equation for inclined pipes, we will subtract this term right here. We can also derive these equations by the same method that we did in the previous section for the horizontal pipes, but it will be very lengthy, and the simple you can do that whenever we talk about inclined pipes and you see the term delta P right here, you just need to subtract this term. from delta P, and you will get the equation for your inclined pipes by just simply modifying a simple modification in the equations of horizontal pipe for the pressure drop, for average velocity, and for the flow rates. So this was our first lecture of FM2. Hope this was clear. See you in the next lecture. Allah Hafiz.